Line integrals continued. All right, so I demonstrated example 1 yesterday. I'm going to demonstrate example 2. So, in fact, let me just write down. So, number 1, which I demonstrated yesterday, had a line integral that looked like this. And then you were given some formula for C. Now, this is a sort of a classic line integral because it's got a ds. Okay? And we turned the ds into dt with the square root like this. It was just 2-dimensional, right? Yeah. All right. But in exercise 2, we don't have a ds, we have a dx. Sin x dx, where C is the arc of the curve x equals y to the 4 from 1 minus 1 to 1, 1. So that is sort of a sideways quartic. If you're just drawing a rough diagram, it'll look a lot like a parabola. But if you draw x equals y squared and x equals y to the 4 on the same set of axes, you'll find that it's actually got a sort of a flatter bottom than a parabola. But just in a rough sketch, you can't really tell that. And we're going from the point, from the bottom point, right? Yeah, 1 minus 1 to 1, 1, like so. All right. So, a couple of things here. One is we have a dx, not a ds. So when we turn the dx into dt, we're going to do that. There won't be a square root. There'll just be one little lonely derivative rather than this square root of the sum of squares of derivatives. And the second thing is that we're going to have to actually parameterize our curve. So let's have a look. R of t equals, well, it's x equals y to the 4, right? So I'm going to call y t, and then x will be t to the 4. And t goes from minus 1 to 1. Okay, so parameterizing my curve. Yet another example of something that early in the course we considered in problems by themselves are now just one small part of a bigger problem, parameterizing curves. That happens a lot. As you get towards the end of this course, the problems become, I want to say bigger. Big is not quite the right word. The problems become more sort of collections. They become more sort of, what's the word I'm looking for here? Requiring a cluster of skills rather than just one skill. Whereas early on in the course we would deal with each skill one at a time. Okay, so the integral that we've been asked to work out is going to be the integral sine x is going to become sine t to the 4. Okay. The dx is going to become dx by dt dt. So the dx by dt is, sorry, not 3. 4t cubed dt. And on my integral sign, I'll have values of t. So t goes from minus 1 to 1. And there you go. And now it's single variable calculus. And not a particularly hard one either, because the 4t cubed is simply the derivative of the thing inside the t, inside the sign. So we know that this is going to be minus cos t to the 4 evaluated from minus 1 to 1. Let me just check myself. If I differentiate minus cos t to the 4, chain rule says I differentiate the outside function first. So I'd get sine t to the 4, and then multiply by the derivative of the inside function. So that's 4t cubed. Okay, cool. So that would be minus cos of 1 plus cos of 1, which is 0. Which is fine. That's not a, I mean, if what we were working out here was something like maths, then that would be a worrying result. But we wouldn't have our density being sine x, because sine x is sometimes negative and you don't have negative density. So given that sine is positive on part of that curve and negative on other parts of that curve, it makes sense that there's been a certain degree of cancelling out. Okay, so that's that. And then number 3, the thing that makes number 3 different from numbers 1 and 2 is that the curve is a union of smaller bits of curves, and also it's using that new form of notation where we drop in the integral signs. Oh, some people are going to sleep. There we go, that's what we were given. C consists of the line segment from 0, 0, 0 to 1, 2, minus 1, and then another line segment from another point to another point. So I'm just going to draw just a sort of a little schematic. And that is 1, 2, minus 1. And that is 3, 2, 0. Okay. So I've actually got 2 line segments there, C1 and C2, where my curve is the union of them. So let me parameterize R1 of t. R1 of t is going to be just, well, okay, C1 is the slightly easier one because we're going from the origin. C2 is going to be the beginning point, 1, 2, minus 1, plus t, end point minus beginning point. So 3 minus 1, 2 minus 2, 0, subtract negative 1. It's going to equal 1 plus 2t. I don't have to join them together. Generally, if I were describing a line or a line segment, I actually would not join these 2 vectors together, because that look of point plus parameter times direction vector is a good descriptive look for a line or a line segment. But given the use I'm going to be putting these curves to, it's convenient to combine them in a single vector.
Ma'am,
Yeah?
how do you know, like when you do T1, you assume that t is 1 when it's at the point 1, 2, minus 1, and that t is 0 at point 0, 0, 0. How do you know that?
Whenever you define, so you can always parameterize any curve in multiple different ways, and that goes for lines and line segments. But a convenient way of parameterizing a line segment, remember, okay, I'm going to do a bit of a digression here into first year vector geometry. Let's say you have some point, and let's call it point A. And over here you have some point also on the line, and you call it point B. And you want the equation of that line. The equation of a line is point plus parameter times direction vector. And we get that direction vector by subtracting those 2 points. And if we subtract those 2 points, we can think of that vector that we've created as an arrow that goes from the one point all the way to the other point. So one unit's worth of that arrow will take us from A all the way to B. So if I rub this out, I'll rub the whole thing out. If we actually wanted a line segment, not a line, if we only wanted that line segment from A to B, then our line segment would be A plus parameter times this direction vector. I will call this direction vector, what shall I call it? Let me call it V. My point plus parameter times that direction vector. And if I only want that line segment, by definition pretty much, I want my parameter to go from 0 to 1. Because 0 means I haven't gone anywhere, I'm still at A. And 1 means that I've gone 1 unit's worth of that arrow, which means I've gone all the way to B. Because that arrow is defined pretty much as the distance, but with directionality built in, between A and B. if I got that arrow by saying b minus a, it means the arrow is as long as the distance between a and b, and therefore one jump's worth of that arrow will take me all the way to b. So I don't know if that's answering your question. But when I'm parametrizing these line segments, it's kind of built in. The fact that I'm getting my direction vector, the thing that's sitting after the parameter, the fact that I'm getting that direction vector by taking the end point minus the beginning point means that if I'm wanting the line segment, I want my parameter to extend from 0 to 1. Of course, I don't have to take my direction vector as that full arrow. I could take it as half the arrow, a quarter of the arrow, or double the arrow, in which case my parameter would not be from 0 to 1. It would be from 0 to 2, or 0 to 4, or 0 to a half. But if I'm using as my direction vector end point minus beginning point, then it's built into that geometry that I want my parameter to extend from 0 to 1. Sorry, that was probably a lot more than you wanted, but did it address your question? Cool, good. I know people do struggle to parameterize line segments, and while there are things in life worth struggling with, parameterizing line segments is really not one of them, because it really is quite easy. It's point plus parameter times direction, and if you got that direction by saying end minus beginning, it means your parameter you want to go from 0 to 1. Question?
How do you put t as the element of 0 to 1?
I beg your pardon?
Why is t element of 0 to 1?
Because 0 means that t equal to 0 would keep me at my beginning point of my line segment, and t equals 1 would take me to the end point of my line segment, because the length of that arrow representing the direction vector goes from the beginning to the end.
So it will differ depending on which segment you have.
So I've got two line segments. So I've got two line segments which I've parameterized separately to one another. I have to. In each line segment, I've followed the same procedure, which is I've got my direction vector by taking end minus beginning, but obviously the end and beginning are different for each line segment. But because I've followed that same procedure of end minus beginning to get that direction vector, it means t goes from 0 to 1 for each of them. But they are two different curves. So that's curve 1, and that's curve 2. So for your own just sort of symbolic comfort levels, you might actually even want to choose a different letter for your parameter to show that it is a different curve that you're talking about. It doesn't actually matter using the same letter, but as I say, possibly you might actually want to choose a lambda or an s or something for one of them, just so that it's really symbolically clear that you're dealing with two different line segments. We can't parameterize the full curve with a single parameterization. It's not possible. Okay, alrighty then. Yes, another question, yes.
What is your reason for changing it from the line to the three?
I'll bring it together.
Yeah.
Because I know I can look just a little bit into the future. I've said before, as a mathematician, it's always useful to be able to see just a little bit into the future. And I can see that I'm going to have to work out a dx by dt, a dy by dt, and a dz by dt for both of these curves. And therefore, it's helpful if I can have my x parametric expression and my y parametric expression and my z parametric expression nice and clearly sitting in front of me, rather than having to do some work combining vectors as I go. All right, so let's actually do the integral, and then you'll see how it all comes together. Equals. Okay, so this is going to be longish, simply because of the two curves. So first of all, for the first curve, I want x squared, which is t. In fact, you know what? I'm going to go back to my R1 over there, and I'm actually going to bring the t inside the brackets. You don't have to, but for the same reason as I just described for curve 2, it's nice to be able to see the parametric expressions nice and clearly. So x squared is t squared, but then I want a dx by dt, which is 1, plus y squared is 2t squared. I'm wanting dy by dt, which is 2, plus z squared is minus t squared times by dz by dt is minus 1, and all of that gets a dt, and t goes from 0 to 1, and that is curve 1. Okay? Plus, I now have to do that same thing over again for curve 2. So for curve 2, x squared is 1 plus 2t squared, dx by dt is 2, plus y squared is 2 squared, dy by dt is 0. That's nice. Plus z squared is t minus 1 squared times dz by dt, which is 1. All of that gets a dt, and we go from 0 to 1. And that's interesting because both of those long integrals have a dt at the end, and both of them have the same limits of integration. So actually we can scrunch them together into a single integral, which wouldn't necessarily be the case. If t went from, say, 0 to 2 pi, or 0 to pi or something on curve 2, we wouldn't have been able to combine them. But there's just sort of happenstance that we can in this case. Okay, let me tidy up a little. That'll be t squared plus 8t squared plus t squared plus, let's have a look, what'll that be? That'll be 1 times 2. That'll be 4t times 2. That'll be 4t squared times 2. That'll be a 0. Let me actually just write plus 0 so you can all follow where I am. And then that'll be plus t squared minus 2t plus 1. Whew, what a lot of terms, but they're all very simple terms. So where's all that coming from? All of this is along C1, and all of this is along C2, and this bit here is the C1 part, and this bit here is the C2 part, but we don't have to keep them separate because now it's just an algebraic expression. We can just scrunch the things together as makes us happy. So let's have a look. That'll be, how many t squareds do I have? 1, 9, 10, 18, 19. 19 t squared. Is that right? I'm not remembering the number 19 from this problem. None of the t squareds are minuses. That's a 4, that's an 8. There's a 1, there's a 4 times a 2 is an 8. Let me just finish writing down, and then if I've made a mistake, I'll go back and find the mistake. But let me just finish writing down for now. There's an 8 and a minus 2. And that's a 2 plus a 1. T squared. And, is that a oh yes, it is a minus. It is a minus. It is a minus. I was thinking, of course, when we square the minus t, that minus disappears, but of course the other minus doesn't. So that is a minus. And so it's actually 17, not 19. Eight and 8 and 1. Yes. Yes, now it's right. I'm pretty sure. Okay, so what do we have? We have 17 over 3t cubed plus 3t squared plus 3t from 0 to 1, which is 17 over 3 plus 3 plus 3, which is 3 and 3 is 6, and 6 is 18 over 3, and 17 and 18 is what, 35? Okay, that was just, not only was it single variable integration, it was polynomial single variable integration. So, I mean, frankly, you could have done that in high school. So, there wasn't really a lot of hard work in this problem. There was just knowing what to do with a line integral, which is really just plug the stuff in. and there was parameterizing line segments, or parameterizing a curve. Question?
You said we could write T, you could have for curve 1, the variable can be T, and then the other one could be like S or something. Now, if you would have done that, how do you combine them?
Then you wouldn't combine them.
Solve them.
Yeah. So the question is, if we had actually used a different letter for our parameter, say curve 1 we used parameter letter T, and for curve 2 we used an S, then our second integral would have been full of S's, not T's, and we would have kept them as two separate integrals rather than combining them, but we still would have ended up with the same numerical result right at the end. And in fact, I notice in the solutions that I typed up, I actually, even though I used T for both, I actually didn't even combine them. So it's not something that you have to do. Okay, why don't you give it a go? You try number 4. Now 4a is actually the same as question 1, but how about you see if you can do it without looking at the solution that I did for number 1. I'll write up the answer so that you can check yourself. And I'll give you, how many minutes should I give you? Not the rest of the lecture, no. Okay, your answer for A. Answer for B. Ooh, the answer for B is really chunky. And the answer for C is what? All right, line integrals and work. Work done. Okay. So we have seen in this last section line integrals for multivariable scalar functions multivariable. So there have been multivariable functions, but there have been multivariable scalar functions insofar as there haven't been vector functions. You'll put in your domain, but what you'll get out is just a single scalar value. You won't get out a vector. F of xy or f of xyz. Okay. However, line integrals can also be determined for vector valued functions. Line integrals can also be determined for vector valued functions. Such as okay, so here what you're putting in is vector. You're putting in x vector, xy vectors, but what you're getting out is also a vector. Okay, so F would be measuring something like velocity of flow or something like that, or like a gravitational field or a magnetic field or some sort of field. We define the line integral of F, a continuous vector field, a continuous vector field on a smooth curve C. So this is all the terms and conditions here. Defined by, okay, so we've got C and we can parameterize it. into something we're calling R of t, where t goes between a and b, as, okay, so here's the definition of a line integral for a vector valued field. F, so here's the first difference, very similar notation to what we've already had, but there's a dot in there, and it's not ds or dx or dy or dz, it's dr, and then the little r's got an arrow on top, okay? So that makes it similar to our flux formula. Remember our flux formula had a d big S with an arrow on top. Okay, and that is equal to, okay, I'm going to write down something and then I'm going to justify it. So f will generally be in terms of x and y and z, but our curve is parameterized, and x is a function of t and y is a function of t and z is a function of t. So into big F, which is full of x's and y's and z's, we can substitute our parametric expressions for x and y and z, and hence we've got f of r of t. So that looks very fancy with all those brackets and arrows, but basically it means you take your big F full of x's, y's and z's, and you make it full of t's by replacing the x's and y's and z's. And then here is the bit that's going to look a bit strange. Let's have a look. I just want to make sure that I'm writing this correctly. Okay, and I'm going to dot with r dash dt. So let me justify why that is the case. Okay, dr basically stands for the vector dx, dy, dz. Okay. Okay, so that dr over there. Okay, so we're taking f and we're dotting it with the vector dx, dy, dz. That's what the vector dr is. Okay, but we can kind of play a mathematical trick here. And do that. And as I said yesterday, on the one hand that looks very logical because it looks like you've just multiplied by dt and divided by dt, but that's not really what you've done, because those are not fractions even though they bear a resemblance to fractions. But playing those sort of games with differential operators actually does work, and it's not incidentally related to the fact that that notation represents the limit of a rational expression. So the fact that that notation, that you can manipulate that notation in very similar ways to the ways you manipulate fractions, is not accidental because of the sort of historical roots of the notation. Okay, and that thing in brackets is r dash. Okay, what's the time? What we normally see is something like this. So we normally have big F being a function of P, Q, and R. And so then the line integral of f dotted with dr is, we can take that vector pqr and we can dot it with the vector dx, dy, dz, and we get this. Okay, so I suppose what all of this is that I've just written down is kind of a cluster of different ways of writing, of expressing the line integral of a vector field. You can write it as that thing that's up at the top left of the screen over there. You can write it as the integral of f dot dr. You can also write it as that thing at the top right of the screen, as f dotted with r dash dt. Same thing, different way of writing it. But also, this thing down at the bottom is also another way of writing your line integral of f, where you've actually carried out the dot product between big F and the vector dx, dy, dz, and you've ended up with something that has 3 terms in it. And we use that funny notational ploy of dropping the integral signs. So these are really, this is not really, sometimes you start off with an expression and then you kind of progress and you achieve a new expression through some sort of logical process. This isn't really what's happening here on the screen. I'm kind of just showing you 3 different options for writing down the line integral of a vector field. They're all equivalent to one another, and sometimes one is more convenient than another. Okay, the most important application of line integrals of vector fields is work. Where the line integral of f dotted with dr is the work done by some sort of force field, very vague wording there, and moving a particle along curve C. Okay, and then I would like to demonstrate with an example, but it doesn't really make sense. We only have 1 minute left, so I'll stop there and I'll demonstrate with an example tomorrow, and then you can do one, and then we're moving on to something called, well, we're not moving on, we're staying in this area of work done, and we're looking at some special cases of things called conservative vector fields, potential functions, and path independence of line integrals. Okay, some nice big words for you to impress your non-mathematical friends with.